Hello, everyone. I'm Liang Chen. I'm an associate professor from Jiangsu University of Science and Technology. I received my doctoral degree at Shanghai Jiao Tong University. From that time on, I have dedicated to research work on biomedical titanium alloy. It is my great honor to present over this forum. This forum was initiated by the BME Horizon Journal. BME Horizon Journal is an international peer-reviewed open access journal published quarterly and owned by Science Exploration Press. The journal is dedicated to advancing research and innovation in the field of biomedical engineering applications. The journal provides a platform for cutting-edge research that bridges the gap between engineering, biology, medicines, and environmental science to address challenges in healthcare and sustainability. Here is a piece of good news. BME Horizon has no article processing charges for papers accepted before the end of 2029. Contribution to BME Horizon are highly appreciated. Today, we invited a world-famous scholar, Professor Laichang Zhang, to give us a lecture of 3D printing of biomedical titanium alloys. Professor Zhang is head of Center for Advanced Materials and Manufacturing at Edinburgh University. His research interests include metal additive manufacturing, metallurgy, biomaterials, light alloys and structures, and high-strength alloys and composites. He is a highly cited research and advanced materials lottery with approximately 410 journal articles, an H index of 93, and more than 32,000 citations. We also invited a guest, Professor Gao Xiao, to attend the discussion sections. Professor Xiao is a tenured associate professor and deputy director of the Department of Environmental Science and Engineering at Fuzhou University. Professor Xiao is recognized as a high-level talent in Fujian province and Quanzhou high-level talent in higher education. Professor Xiao has presided over 12 national, provincial projects, published over 50 articles in renowned journals such as Science, Peanuts, Biomaterials, Nanoletters, and served as a young editor board member for Nanomicroletters, International Journal of Molecular Sciences, and BME Horizon. Now, let's invite Professor Zhang to give the lecture. 好，张老师到你了。
First, many thanks, Professor Chen's introduction, and also the general BME Horizon's invitation to give this opportunity to share with my colleagues and friends some knowledge and all the topics on the research of 3D printing of biomedical titanium alloys. So I'm Lachun Zhang from Edinburgh University from Perth, Australia. So this is my information, so email and telephone number, and also you can scan the code from my official working web page and also Google Scholar and all the suitable information to get some details of my research and also my publications and also some other related information. So for this topic, so most will be on the biomedical titanium alloys. So why we need some titanium alloys? Because titanium alloys are quite common and very popular in the field of biomedical applications due to their high corrosion resistance and also lightweight structures. But the one thing for some patients, so the offshore of the shells implant do not provide a suitable clinical outcome because of injury, diseases, and also previous implants. For example, there's existing shoulder replacement and also these implants on other materials. So for these kind of reasons, so we cannot use the shell standard material and cut off from the structures. So for these patients, customized implants may be the preferred solution. But how these customized implants should be produced if they are manufactured by machinery? So then for this kind of things from the material of aluminum, for example, of the shape of the bars or plant or plates, there would be a lot of waste of the raw materials used. But keep in mind, because titanium material is quite expensive, and for this kind of waste of the material, only about 25% of materials utilization of such kind of expensive material, especially for titanium, is quite expensive and the cost of the money from the patient. So therefore, for 3D printing or additive manufacturing is one better option. Especially, for example, this for injury or disease, this is one real example. So from our customer, so from Royal Perth Hospital. So this example of manufacturing of a customized implant for a patient with osteoporosis. After operating, we achieved the information from the CT scan, other information or BMI. So we can get information of the burn. So you can see a lot of materials for the burns have been bruised, that's upon the holes. So after we get this information, we can design this kind of thing. We can put the structure, and we can replace this kind of height of these things. Then we can put some nails or screws. We can put the brands, and we can produce. So that's this kind of structure is just specific for the patient. So far, there's some materials that can be used for the structures. Most of them for commercial purity titanium alloys, and also titanium 6 aluminum 4 vanadium. So most of we used for the implants to replace our cortical burns for human beings. But because there's a lot of difference from the Young's modulus or stiffness from the cortical bone and also for titanium alloys. So this kind of thing we have produced the well-known or famous stress sheeting phenomena. And then this thing will need a further surgery to fix these kind of structures from the implant. Of course, there's another way to do so. These things can produce or develop low Young's modulus of titanium alloys to match the Young's modulus of cortical bones. For example, TNTJ gang matter TR2448. So this famous beta titanium alloys, they have a very close Young's modulus compared to cortical bones. But this DS higher, so you can see this will go to roughly 30, and this one could double or triple for these things. So even it's a better or lower Young's modulus, but still high. So of course, for this kind of way, we can still use when we use produce porous structures to further reduce their modulus. So for this kind of thing, we need further optimize of this kind of structure produced. And of course, these complex porous structures can only be produced by 3D printing. So for example, selective laser melting or electron beam melting. Of course, there's also transition away from the powder metallurgy of these things. So when we try to make anything here, so we produce these structures of these things. So of course, you can see that this kind of beta titanium alloys, we can put most of them titanium. We started from the spherical particles from TR248, so TR24 niobium, for zirconium at 18 for this alloy. So of course, we can from the powders, so we can produce the structures. We use a 3D printing, so they can produce the Young's modulus. We should use the the parameters from processing. So for example, the laser power and also velocity of a laser scan, and also hatch spacing, and also layer thickness. So that's with the parameters. We use a zigzag pattern to produce 3D printed parts from the powders for titanium cubes or structures. So of course, based on these things, we should know. So the relative density is quite expensive, very important to get the high performance in mechanical and also corrosion resistance. So for example, if we get the structures lower, so now the strength will not good enough. And of course, that's why make premature fracture. So that's why most of the structure we try to make the solid part from more than 99%. So that's why we get this information. So we get the different parameters. So we can see this with the laser. So keep as a 200 watts, and then we can see reducing the speed, scan speed, we can enhance the relative density, go to 99% of platinum. So that's stabilized here. So, but we can further decrease the relative density, the laser scan speed, and then the relative density will be further decreased because this is already overheated of the parts because the engine too large and it will overheat, and also get some bore meanings and boring information, so that they get a lot of bores on the side. It will reduce this the structure. So that's the one thing, but we can still see the macro hardness tests will still increase with the relative densities of these things. It go to really high. So, but we can see what roughly we get this thing if the scan speed will be roughly below, so 600. This can see the relative density will go to 99%. But we try to make this one come in the industry, so for commercialization. So that's why we try to get a large processing windows to make the parts with a high relative density more than 99%. So we produce a lot of different parameters that we can find the relative density of this energy density of these things. We can find for energy density roughly 33 joule per cubic meters. We can produce the parts with 99% of the structure. So of course, we can still consider microstructures of the produced parts. So in the three representative conditions. So that's for the near fully density at 550 millimeter per second, and the wide is intermediate density or at 650 millimeter per second, and with a lower density, so at 800 millimeter per second of these things. So when you see with a really fully density, you can see only see the laser track. So this is created during the selective laser mating processing. So of course, this one is presented by dark bands, so are clearly visible in all microscope. And these tracks are typically microstructure features in samples manufactured by 3D printing. For the nearly fully density of the parts, the powders have completely melted or defined, and there's no apparent porosity in the microstructure. But for the samples with the intermediate density, unmelted particles are evident in the microstructure. You can see there's still incomplete particles. Therefore, it may be concluded that the laser density was not sufficient to completely melt all of the powder particles. In the samples with the lowest density, the numbers of the unmelted particles you will see here has increased, and the porosity is clearly presented of this kind of parts. They also produce an example of acetabular prosthesis by selective laser melting at a laser power of 200 watts and a laser speed of 550 millimeter per second, because they can get near this fully density of the parts, so you can see the parts. So this one we collaborated with the Royal Port Hospital. The card has a complex and a fine scanned scaffold structure on its outer surface, which is improving burn in growth implants of this structure. And of course, we can see the comparison of the tensile properties for the TR248 alloys, so manufactured by 3D printing and also by conventional processing methods. So you will see the Young's modulus is quite low, so roughly, so you can see so 53, and this is very close to the produced parts from the traditional, so from the hot forging and also further hot rolling of these things. But the key thing is that you can see that the strength is almost the same of this thing because this one is after casting, forging, and further rolling. But we didn't put anything, but I can see the strength is very, very comparable. And also is considered ductility. This is the globally, there's a first part with a large ductility compared to the traditional parts. Of course, we also produce a lot of parts of these things from the titanium, niobium to parts from the powder mixing. So because this one from the powders of the pre-alloyed, but we still can use a lot of them from produce a lot of them for mixed powder. We try to make the parts cheaper. So we try to mix a lot of mixed powder, and you can see the strength is very, very large, and also ductility is also large of these things. We didn't do many, but you can see that the ductility is quite large compared to the traditional way. So that's will be very, very good. We can go to more than 20% of these parts, just produce the parts with a low cost from the traditional way, from the pre-alloyed or from powder mixture of these things. But even this one still with a low Young's modulus, but still high. So we mentioned so the Young's modulus of cortical burns roughly 30 gigapascals, but this is 53, even low, but we can still produce a lot of further reduced further titanium parts with a low Young's modulus further. So that's why from this way can produce 4 porous titanium alloys. And of course, this one can have a lower Young's modulus with control and close to the surrounding burning tissue. And of course, titanium alloys can have excellent biomedical compatibility, and that can be represented for the next generation biomedical implants. So traditional way, we can use the way to produce this kind of power structures from the powder sintering processing, gear casting processing, 3D fiber deposition, and self-propagating high temperature silicates. For this traditional way, but it's one way for this traditional fabrication is one big issue. There are inherent limitations such as presence of impurity phases, low porosity, and limited control over the size, shape, and the distribution of the pores. So that's why from here we had a lot of endeavors to develop new structures of these things. That's what we did in this kind of field. For example, with this apparent, we can do many things. We can produce the structure. That's for example, for traditional layer, grid scaffold. So if I can see here, there's even put anything here with the structures. We can put a layer by layer, of course, we control the thing. But actually, this one's a big issue because these kind of things will produce a lot of inhomogeneous in elastic in Young's modulus. You will see the Young's modulus roughly the latest stiff direction has only about 14% of the stiffness of the most stiff. So this is typically inhomogeneous of the structures. But we can also use for the BCC structure. So this is a structure has also been commonly used, but this is even worse in terms of the non-isotropic stiffness. You can see only the minimum and the maximum was roughly 0.09, so 9% of the stiffness. Now, another one is the gyre water structure has also been used, although it's a better and also have a better homogeneous in stiffness. You will see this minima and a maxima stiffness roughly 0.42. But we still say this is not sufficient isotropic of this kind of structure. So that's what for these things we use the topology optimization to design the scaffold that would have a maximum modulus for its weight and interconnected porosity. In addition, so the design needed to be elastically isotropic and be able to be made in a range of different solid fractions. So we proposed use a computational design scaffold to, let's say, jointly maximize scaffold bulk modulus and diffusivities, of the pore space. This can ensure high scaffold stiffness and a good transport process properties. And also, that's very important because this one will try to make it elastically isotropic. So otherwise, the patient will not have good feeling. So because if a turn, and you can see it's a click inside, it's not homogeneous. So that's why we try to ensure no direction of low stiffness. And also we have a specific porosity because for different structure, for example, if we come to our burns in head, face, and our skull, and also our knees and the shoulders and the legs, arms, of course, the Young's model will be different. We will use one example to show later on. So of course, we try to obtain several designs and different porosities and match the modulus of a burn by choosing an appropriate porosities. For this kind of criteria, so we design several type of the porosity optimization scaffold. For example, we adheres to all the requirements and we have this complete interconnected pore space. This is complicated, but this Young's modulus for all the way is homogeneous. So this is compared for the 70% of the layer with scaffold, it's roughly 0.14. So that means there's homogeneous structures of this kind of way. But of course, there's some examples. This is the unit cell we developed. So, and you see we can from the 10, 20, 30, 40, 50, 55, 60, 65 roughly, we go up to 90% of this thing. We can go to disability. And this is the way, for example, to show the structures. You can see the parts we produce is from 3 by 3 by 6. So you can see we can produce many things of these things. So of course, this one can go to up to 95% of the processes. That means the only 5% of the solid fraction. So that is much high structures. So we can see this structure is very complicated. So you can see that's the support, and you can see every layer is complicated. So you can see the structures will be different. Interconnect, and we can see every layer will be different. This is simulated the 3D printing layer by layer. So that's why I can see the additive manufacturing layer by layer. We can see the structures of these things. We'll see again. So of course, based on these things, we can see the structure we design all of these here. So we measure stiffness of the different materials from the titanium, from bronze, from steel. So, and relative to the range of porosities, and also we can produce of the structure for normalized modulus for the y-axis, and also design the porosities for the x-axis. So for normalized modulus, we can see Young's modulus of each structures for porosity and divided by the 100% of the solid parts. So let's say it's a normalized modulus. Now, of course, we can see the density. So this is the curve. This is the curve that is from the data theory. But we see the data, we use the scaffolders. You can see scattered data, that's for the structures for the titanium, bronze. You can see just very close to the structure itself. So of course, you can see come back to the TR258. You can see this one is Young's model we can control very well. So for example, cortical bronze is roughly 17 to 24. And of course, this one was so for titanium, 6 aluminum fluoride is roughly 110. And for TR258, you can see we can use solid parts. It's a 53, 30% porosity, 30, 50 porosity is 50, and 70 porosity is 7, and 80% is 4 gigapascals. That means we can see this kind of structure can be produced very well. We can control the porosity, and we can control the stiffness of Young's modulus. So that's we can make this one close to the cortical burns. So then we can match for different location. We can see some example of these things. For example, we will try to match the models of the burns. Okay, for example, we try to replace in the cortical burn in the mandible. The mandible, because every day we talk, the chewing, and other things. So that's why this one we need a lot of comfortable things. Of course, the tactile Young's model roughly 10 gigapascals, and okay, using titanium as a scaffold material. For example, you will use titanium 6 aluminum for vanadium. That's your number roughly 100. We say just that's 110. That's just 100, for example. So then from this chart, so we can get some information. How can make this Young's model close to our implant, for example, for the medical modelers. So that's all from here. We can roughly get these things. So you see this target one is 10, and the overall is 100. So 10 to 100 is roughly 0.1. So that's what we can get from chart. We can say 0.1. We can get this data. So then we get this thing to find where's how much of the design prostate should be. So then we can read off that's roughly 70%. So then we can say, hey, this is 70% of the prostate optimized scaffold is suitable for replacing our medical to match the use model of the medical. So that's the work for these things we can see. That's for the titanium from the graph. We can get the data very easily. Same way, you will say, okay, we can use another one. Yes, we mentioned for TI-248 for the beta titanium alloys. Again, we're just replacing the coatable in medical. So again, like just about 10 gigapascal, but this time because of the beta titanium and the use was roughly 50 gigapascal. As we mentioned, it's 53, but this is 50 gigapascals, and then we can also from this chart. So we can say normalized modulus is 10 over 50. So from here we can roughly get it. So 0.2. So from 0.2, of course, you can see this will be very useful. We can see there's a 0.2. So close to this thing, we can from the curve. That's what we can see it's roughly 55%. So then say, so the 55% optimized scaffold is suitable for medical implants. So of course, this one gives the Young's modulus roughly 10 gigapascals. So that's why we can use this kind of thing to mention this structure. So they say, okay, that's so easy. No, don't think that will be easy for us to use, because when you try to get the geometry, not like easy to produce. For example, we try to make a circle. The circle you think is quite easy, but when you try to get them optimized, it's not that easy. For example, let's just give you one example. You will see the down skins of all the holes are rougher. Then I put a comment here, rougher compared to our design smooth surface. You see from different size, you will see from different parameters, you will see the down skins of our holes are different. So that's what this one, don't think that's quite easy to produce the parts as we use 3D printing. We still need a lot of technology. And of course, we need the concepts. We understand the 3D printing, then we can produce this kind of ideal structures. From my way, because these things, I can tell you for this thing from the beginning, we try to make this part as a whole, as a circle. But for the first time, we produce this one just totally closed. There's no open. Then we try to make this one open and ellipse, and then we go to circle. So that's why from here, you can see it's simple, but not that simple. You still need a lot of skills and knowledge to try to make the circles, okay, from the design. So that's because from the 3D printing, the down scales, there's a lot of loose powders, and it's not good for our performance of the particles. And also because there's a lot of overhang, okay, structure. So of course, these things, they can downsize, down skins, there's a lot of roughers of these things. So that's why from here, you still need a lot of knowledge of these kind of structures to make these parts. Typically, if you come to an example of these things, this still will see this for the structure from here. You can see from this structure. If the pattern is not good, you can see the down skin is not as great as we design. And of course, you still cannot see a lot of holes here. So you can see a lot of holes. You can see there's a dark one is a holes. So this is from fabrication. And of course, you still can see the thickness and the smoothness of the strut. That's why you can see the parameters as designed is not as good as we thought. So that's why from here, so I put some conclusion of this part. The volume porosity is reduced by increasing the scan speed, and also the modular process is roughly from 10 to 20 micrometers, and we still produce large pores. That's because that the laser scan speed will be this thing. So even this thing is still a way to optimize. That's why we still need the knowledge to process these things. And of course, you can see there's some parameters. You can see the scan speed of these things will be also where flow thickness will change of these kind of structures. You will see still a lot of things and also kind of structures. The density will change and also the mechanical property will be changed. So that's why from here, we still need a lot of knowledge to produce, for optimize the structures, and then we can produce. Because when the structure is not good, they will produce a lot of holes inside, and then we make this part break much earlier it will predict. That's what we call premature failure. That's because of the insufficient relative density to produce this kind of structure. So of course, we have a lot of way to produce the optimized with high relative density structures, but a lot of processings of the structures. Here is one thing after processing. So we can see that topology for the structures. You can see there's a lot of structure of these things. For example, this was a long body. So the structure of these things, and you can see there's a lot of parts very, very big. So of course, from here, we can see we try to make this one about beta titanium. And we can compare. So for the two popular, so one is electric beam melting, we call EBM, and another one, so selective laser melting, we call SAM. You will see the surface will be different. The microcity image of the single unit cell used for the EBM or SAM, you can see, are showing these things are much, much different from the compare for this kind of structure smooth. But as you can see, the surface will be different. So it's apparent that the SM part has a smoother strut surface than the EBM one. Especially you can see it's much smoother, these things. Okay, and also you can see that from figure C and D, they shows the locations and the distributions of the defects. There's a marked in the red color, one red color inside the solid strut. You can see a lot of the red color. That's the defects inside, and also this is the distribution of the parts. So as you can see, nearly all the defects in the EBM parts are in spherical shape, while those in the SM have an irregular shape, and some even large defects display a cortical-like shape. So now, of course, can make summarize of these parts. We can show the defect count and the size distribution in the EBM and SM producer specimen according to the figure C and D. So you can see the number of defects inside the EBM producer sample is less than the SM manufacturer sample. This is especially true for the pores with the equivalent diameters of these 30 to 90 micrometers. You can see from the color, the dark color, that's from EBM, and the light color is from SM. You see from 30 to 90, the numbers, so you can smaller. Okay, there's a count of this, that's the number of the defects smaller. And also you can see SM is a big parts. Yes, still have a lot of big parts that are produced. So that's way a lot of produce good mechanical properties. So of course we can see the structure. So from the static properties is quite good. So you can see this one have a after we homogeneous. This one still there's no any breaking, just for the shattering of the parts. That's because the structures can be deformed gradually. So that's what it means. These parts have a good tolerance of the values of these things. But also we can see the Young's modulus compared because other the homogeneous the beta. That's also almost a simple or comparable. But the interesting is the fatigue. The fatigue strength of the near EBM and SM are both with the beta titanium are of course sensitive to the stress amplitude. At the lower stress levels, for example, at for the 6 megapascals, you can see this one is roughly equal. So of course, the fatigue behavior of the mesh is mainly determined by the cyclic region and the surface properties of the struts, and then resulting in similar property of both manufacturing process. However, at the high stress level, the crack initiation and propagation from the pores tend to be occur, and also therefore the SM samples, which contains a high number of defects, as we show on the last slides, have a lower and more variable fatigue life. You can see the gap was much bigger. Of course, we can show here some samples of the also have a fatigue striation. So you can see there's a lot of visible. So in most crack regions of both EBM and SM parts. But also we can see the large defect So greater than 100 micrometers in size, and it's marked by the dotted part of this part. So it's also observed on the fracture surface of the near the SM samples. Such defects would significantly decrease the fatigue life of the sample. That's why you can see here, so large gap, so variations of the fatigue life of these things. We also produce a lot of things with a different porosity size levels. As we mentioned, the porosity can be controlled. We produce a lot of things from 20, 30, and of course we go to 90 percentage of these things. You will see all this beta titanium have the super elastic properties, even with the different porosities of these things. So of course, for here, for easy reading, we only the super elasticity of the lattice structures with these kind of levels 78, 77, 77, and 91 has been shown here to clearly show these things. And with the increasing the proteins, you can see the super proteins is increasing because they're fully covered of this. This is still have some overgap, as means still plastic formation of these structures. So let's further see the fatigue properties of the EPM producer TI-248. So let's structures with the different properties of these things. So the SN curve of all samples with the absolute and the normalized stress are plotted in this figure and also this figure. So we see the fatigue life dominated by the properties and the prior level stress. Of course, you can see fatigue life decreasing with increasing porosity for both low and high stress levels. So you can see that's quite easy to understand because the solid parts become smaller if this one, the porosity is higher. So of course, we can still see these kind of structures for this normalized fatigue life, because you can see the TI6 pneumonia for vanadium seems to have the better fatigue life, but actually not, because this one just absolute okay, normalized one for the fatigue stress divided by the yield stress. You can see the TI-248 for 75% will be a higher fatigue strength compared to the TI6 pneumonia for vanadium for the structures. So of course, this one, the normalized fatigue life is better because this one should compare to the properties. Of course, we still can see the different structures. You can see have different mechanical property, and the curve were broken. For this one, for example, for these things were broken for the list, everyone were broken. But we see the strength will be lower compared to the cube and also optimized structures. That's because of the buckling for the cubic structures. It's very low density because of the deformation is dominated by the buckling. Because the buckling is here. So when this one not go to the yield stress, but we're buckling, so this one will make this one broken. But the others were deformed by this one kind of structures. You can see this can be have the structure where both bending and buckling of these things. So that's why we can see the structure can be do these things. And also you can see the superplasticity. We can see from this one we can find will be make it bigger. So that's why from here we can see the 1% to 6%. So loading, unloading, loading, unloading. So if this one can fully repeat, for example, this one, that means this one become fully elastically. Like for us, if we wear shoes, we really want the shoes with a good elasticity. Otherwise, it's feel, oh, that's so tight. It's so tough to work. So the way you can see from here, you can see the cubes and also the topological one, mostly from the first step, they will fully recover. But for the robotic one, this one can have some plastic formation because not still open, but fully restored. And then go further for 2% of these things, you will see they go further, and also this one, the cubic one, like even further of these things. Okay, that's why you can see the structure of these things. But we still can compare for these things. We make a summarize of this part. So that's why you can see the edge for these things. We can try to get this. You see the curve loading and unload. So that's why if this one not fully, this one still have a gap. That means this one is a positive. This positive formation occur. That means the positive energy is here. We go under the curve like this. But of course, under these things will be elastic energy as a fully recovered. So from here, if we see it is fully covered, that means that no or limited plastic deformation has taken place. So that's why from here we can see this the elastic deformation. So now from here we can get the information. So we can give in parameters. We can get it from different way. We can get the data for the total energy. So total energy, that's because with the elastic deformation and also the plastic deformation. So of course from the curve, so this one is higher and large, of course that have more totally or total energy of it because the elastic deformation and plastic deformation of these things. So because of the high strength and the large ductility. So that's why from here we get the idea, but we must care about the elastic energy because this is energy absorption. So that's why from here we can get anything here. You can see topological one will be large. So you can see for large elastic energy. So that's why it's good for replace of this thing. Still, we can compare for different materials. This is for TLM. So this is TR25 niobium, 3 zirconia, 3 moly, and 2 tin. And we compare with this thing. You can see for titanium 6 aluminium, this one is a cubic structure, but we can see for TLM, this is the beta type. There's no any layer-wise crack, but just a gradually deformation. But when we come to the TR6 aluminium for vanadium, you can see it's a layer. This one layer crack. So that's why from here you can see these are structures of these things. It's a layer-wise crack of these things. That's because of alpha base inside. So that's why from here we can get the structure, and then of course from these things we get the data of this thing. But basically we can see there's always broken like this way. So you can see titanium 6 aluminium for vanadium for 50%, but for TLM, this beta phase is just gradually deformation, then close. That's why they can go further. So all these things, we can see for beta titanium alloys from these two types of beta titanium alloys. So you can see there's no layer-wise crack. So for the beta titanium alloys, so that's a non-layer-wise fracture for the titanium alloys. So this is the structure is quite good and also material. Still, we can compare for the unit cell and the materials compare for the properties. You will see from here this titanium and for CP titanium, for commercial pure titanium, and titanium 6 aluminium for vanadium. But we can see this kind of structure will be, you see the structures with first part will be fair from here. So even from optimized, you can see this optimized CP titanium, optimized titanium 6 aluminium for vanadium. For these two, you can see this one is a beta. You see the CP titanium is a beta, which is for the first layer, correct, much delayed structures. But you can see also get further for the robotic one, you get further for the CP titanium. That's why the structures will affect the value of the parts. So that's why for even when put everything, for example, we try to input the scaffold in our burns, for example, for mandible and also hips. So that's called, we should consider the structures for these things. So these things we can compare for the structures, and we can see all the things can produce. And that's why you can see the first value is very important because we see where they will fail. So that's why you can see from the first crack. So this one, titanium 6 aluminium formula is not good. It's compared to CP titanium, other things quite good. So it's different. So still we can compare the fatigue life from the other things. For example, here the left two figures show the fatigue SN curve of the topological, optimized, and the robotic structures. The fatigue life increase with decreasing the applied cycle stress. Of course, the fatigue strength and the normalized fatigue properties. That means the fatigue stress divided by the yield strength of the robotic one. So you can see it's significantly lower than those of a topological one. So that's why topological one with a better fatigue life and the fatigue property of these things. Of course, that's why for here we can show in the right figure. So it also can than those of the other reported parts. So that means this one have a diamond, so and other things, and also square matches. So that's when topological one most have a good properties of the structure. So basically, so that's the structure. Of course, we still work a lot with the corrosion and the biocompatibility with Professor Chen, and also my student will do it. But because of time, we cannot make so many details inside. So you are keen to know the more details, you can search for my papers, and also you can send me a message, get information. So finally, I just would like to thank my colleagues and students so for the work for this topic. And also they get two Australian Research Council and also some from most and National Science Fund for these things. And of course, the more details you can see from the publication. So one is from the 3D printing of from the biomedical titanium alloys, and also for the lattice structures with Professor Chen, and also this is from Jiangsu University of Science Technology, and also with the one with Professor Yuhua Li, so this is from Xi'an University of Science Technology, and also this is with the Shanghai Jiaotong University with Processing Module Science. So that's they give more details inside, and they get more broad and the details and a lot of data. You can compare from the 3D printing of biomedical titanium alloys, from the design, from the basic. For example, here we say essential, and we can get more details from why we design these things, what kind of properties for the bone of human beings. And also we can see from the 3D printing, from the different structures. So we can see there are a lot of samples produced by 3D printing. So that's could have a good mechanical property for decay life and also biocompatibility. Okay, that's all for today's presentation. If you have any question, I'm happy to answer any question. Thank you very much.